Let us answer word problems under applications of derivatives, focusing on related rates. For example, the surface area of a snowball decreases at a rate of 7 feet squared per hour. How fast is the diameter changing when the radius is 4 feet? Let's identify the given data in the problem. We have the derivative of the surface area of the snowball with respect to time equal to negative 7 feet squared per hour. It's negative because the change is decrease. We have a given radius which is 4 feet. Then we're looking for the derivative of the diameter with respect to time. So what formula relates surface area with diameter? So a snowball is a sphere. So we use the surface area of a sphere which is 4 pi r squared. But here we see that instead of diameter, we have radius. So we use the concept that the diameter is twice the radius. Hence, the radius is diameter over 2. And we can replace this r here with d over 2. Then we have the surface area is equal to 4 pi d over 2 squared. Simplifying this, we have 4 pi times d squared over 4. Then we can, that's 4. We can cancel 4. Then we have the surface area is equal to pi d squared. And this is what we will differentiate with respect to time. So we have the derivative of the surface area with respect to time is equal to pi. Then derivative of d squared with respect to time will be 2d. Derivative of d with respect to time. Let's plug in the given data. We have negative 7 equals pi times 2 times, so what is d? Okay, since d is twice r, so d is twice 4 since the given r is 4 feet. So that's 8 feet. So times 8. Then dividing, we have negative 7 is equal to 16 pi dd dt. Then divide both sides by 16 pi. So we have negative 7 over 16 pi as our derivative of the diameter with respect to time. And that is approximately negative 0.14. So the derivative of the diameter with respect to time is negative 0.14. The unit of measure will be feet over r. Next example, the side length of a square increases at a rate of 5 inches per second. How fast are the area and the perimeter of the square changing when the side length is 7 inches? Let's identify the data given in this problem. So we have the derivative of the side length with respect to time as positive 5 inches per second. Positive because the change is increase. Another given, we have the side length S is 7 inches. And we are looking for the derivative of the area, the change in the area with respect to time. And also the derivative of the perimeter with respect to time. So let's have first the area. So we're dealing with the square here. So the area of a square is S squared. Then let's differentiate this with respect to time. So we have the derivative of the area with respect to time is equal to 2s ds dt. Then plugging in the data that we have, then dA dt is 2 times we have the s and we have ds dt. We have 7 and we have 5. So the derivative of the area with respect to time is 14 times 5, that's 70. So that is 70 area. So that's inches squared per second. So as the side length is increasing 5 inches per second, the area is increasing 70 inches squared per second. Let's now proceed to perimeter. So again, a square, that's what we have. So the perimeter is equal to 4s. And this is what we will differentiate with respect to time. Therefore, we have the derivative of the perimeter with respect to time is just equal to 4 ds dt. And plugging in what we have 4 and ds dt is 5. Therefore, we have our dp dt as 20. So that is 20, since we're dealing with perimeter, that's inches per second. So again, as the side length is increasing 5 inches per second, the perimeter is increasing 20 inches per second. Next example, a spherical balloon is inflated with gas at a rate of 1,200 cubic centimeters per minute. How fast is the radius of the balloon changing when radius is 15 centimeters? Let's identify the data given in the problem. We have the derivative of the volume of the spherical balloon with respect to time as 1,200 cubic centimeters per minute. So it's positive because when we inflate a balloon, the balloon's volume gets bigger. So increasing in volume. So we use positive. Another given is that the radius is 15 centimeters. So based on this problem, we're looking for the derivative of the radius with respect to time, since it is asking for how fast is the radius changing. So you think it's positive or negative? As the change in volume or as the volume increases, what happens to the radius of that spherical balloon? So what formula relates the volume with the radius? So again, we have a sphere. So we use the volume of a sphere. So the volume of a sphere is 4/3 pi r cubed. And this is what we will differentiate with respect to time. So we have the derivative of the volume with respect to time is equal to 4/3 pi. They are just constants. Then we have 3 r squared dr dt. We can actually cancel the 3 here. So we have dv dt is equal to 4 pi r squared dr dt. Let's plug in the data that we have. We have dv dt given as 1,200 equals 4 pi, and we have a given r which is 15. So that's 15 squared dr dt. Let me write our equation here. 1,200 is equal to 4 pi. Let's simplify 15 squared. That's 225 dr dt. So divide both sides by 4 pi times 225. And we can cancel this. And we have our dr dt as 0.42. So that's 0.42. We're talking about change in radius with respect to time. So that will be centimeters per minute. Next example, the side lengths of a cube are increasing at a rate of 4 centimeters per second. How fast is the surface area and volume increasing when the side length is 8 centimeters? Let us identify the data given in this problem. We have the derivative of the side lengths with respect to time as 4 centimeters per second, since the side lengths is or are increasing at that rate. We have a given side length which is 8 centimeters, and we're looking for the derivative of the surface area with respect to time, and also the derivative of the volume of this cube with respect to time. So let's start with the surface area. So the surface area of a cube is equal to 6s squared. So this is what we will get the derivative of with respect to time. So we have the derivative of the surface area with respect to time equals, that's 6 times 2s times ds dt. Just plug in the data that we have. That's 6 times 2, s is given, and also ds dt. So s is 8 centimeters, ds dt is 4 centimeters per second. So we just multiply them and we get the derivative of the surface area with respect to time as 384. So that will be 384, its surface area. So that's centimeters squared per second. Let's now have the volume of this cube. The formula for volume of a cube is S cube. And this is what we will differentiate with respect to time. So we have dv dt is equal to 3s squared ds dt. And plugging in the data that we have 3, we square the side, and ds dt. The side is given as 8. And we actually have ds dt. So ds dt is also given, it's 4. So we just multiply everything. So we have dv dt is equal to 768. So that's 768, we're talking about volume here, so centimeters cube per second.